Nadia Nassif is a PhD student at the Department of Civil and Environmental Engineering at the University of Sharjah, UAE, and is a grad research assistant in the Research Institute of Science and Engineering, was not able to join us today. So she asked if I could please present her slides since she worked so hard on putting these slides together. So I am not an expert on this topic, but I'll be more than happy to help a fellow PhD student, female engineer, to present some of their works, and maybe among ourselves we can probably see what information is presented in here. I'm probably going to be presenting it this way. The introduction in here is fiber-reinforced polymer bars, and she's going to be looking into how that is modeled with different approaches. She's talking about what the effects of what the ability of being able to have fiber-reinforced polymer bars in construction. She's also mentioning in here the different documents that she looked into that, and then of course the ACI 440 document, ACI 440.1, and the Canadian standards. And then she's indicating that due to the recent advances in the FRP field, it's important to be able to consider durability and serviceability. Looking at serviceability, and then again, this is a topic that we are very much interested in our 440 committee. So she's indicated in here how in many instances when you are designing a GFRP reinforced element, serviceability criteria is controlling. And part of the way of how serviceability is measured is by having equations that control the crack width. Now, that is very important when you have a reinforced concrete structure that has a steel reinforcement. In this case, with the GFRP reinforcement, there is some changes in that, and what she has in there is the equation that she compares the ACI 318 equation for steel reinforced concrete, steel reinforcement versus the ACI 440 equation that deals with GFRP bars. And I think the focus of her is to look at this K sub B, this bond-dependent coefficient K sub B, and be able to look a little bit more in depth into that. So as part of her background information in here, I see that she has listed the new 440 code, 440.11, and she's indicating quoting from a section on the code where the bond factor is defined, and is in this case defined to be taken as 1.35, and the explanation that comes from this document. So the background information that she has is the equation that was used to be able to derive these numbers and be able to be used them for design. And I'm just looking at this. So if anybody has any questions, we could probably refer back to her about what that she's using. I think what is interesting in here is that she's looking into that background test that was done to be able to determine K sub B. And I'm looking in here that she's listing the Canadian standards as the Annex Annex S for the test method for determining the bond-dependent coefficient of FRP rods. Moving into literature review, she references work by Mehani et al. That is looking at the cracking behavior of 15 concrete beams reinforced with glass and basalt FRP, and how this study was able to evaluate those K sub B values. And the conclusion showing in here that there is a minimal reference in K sub B for different bar surfaces when you compare sand-coated and groove, and how a recommendation was made of using between 0.9 to 1.1 K sub B for both surfaces. And I see that Carol Shield is here in the audience, so she probably should be the one standing here and giving this talk. All right. Despite attempts of previous studies to evaluate K sub B, there have been very minimal efforts that were directed toward relating K sub B to other FRP concrete bond relations. And one relationship that is indicated in here is how you relate it to tau sub U, to the bond strength. And then she's now mentioning the STM D7913 test that has to deal with FRP pull-out test. and indicates that this is a relatively simpler standard test method compared to K-sub-B for large-scale testing. So finishing the literature review, there's now coming into, I think, what is the interesting different thing that she is presenting is now looking into machine learning. So I think what her presentation is about, how is using some of these tools for machine learning to be able to poke a little bit more in depth into K-sub-B. Showing how machine learning has been used to be able to model bond strength, and how they have been able to get a good prediction and accuracy with respect to the equations in 440.1. And then it comes also the topic of artificial neural networks, techniques, and how that also can be used to poke into models and be able to assess a little bit more into information based on the results that you have already obtained. So the objective of this presentation is to be able to show how you're going to be using some of these data collection from how to use these machine learning techniques to look a little bit more in depth into this K-sub-B effect and the bond. And let's see what she got. So here's the slide on methodology. Looks like they have a two-stage approach to understanding the FRP concrete bond. The first stage, like with many machine learning techniques, is you collect the information needed for your model and you train your model. So I think that's what is shown here on my left side. And once you have that information, then you can go into step 2, which is to relate all the bond coefficients, the K-sub-B value, to the bond strength. So I think we're going to be seeing how she goes from all the different steps. I see stage 1 has 3 steps, stage 2 has 8 steps, and at the end of that you have a relationship where you obtain theta sub u from the model, how that correlates to the collective value of K sub B. Here's the stage 2 that's described for you, and I see here that she used 29 large-scale K sub B tests. So it would be nice to poke a little bit into this paper and then kind of be able to see the information that she collected and how that was able to be used for her models. Okay, here's where I am just basically showing you the slide. It's a general description of the machine learning models that were used in her study. No notes. Notes. They're all hidden. Yeah, can you explain that? No, let's just go to the next one. So this is the methodology. This is the statistics of the test that she used for her modeling. All right, and then we come to results and discussion, and he's showing in here 3 different steps. One step in here is the Gaussian process regression, and she's indicating that it outperforms and achieved the highest accuracy with an R-square value of 0.95, so it seems to be pretty good, getting closer to 1. The lowest RMS value of 1.18 megapascal, and is surpassing the models ANN and ET. And now once you take that information and now you do a comparative analysis, it shows that GPR and ANN have shown a very conservative prediction and have a 28.9% lower RMS values than ANN. And it shows how it has a superior predictive capabilities for tau sub u. So if you look in the slide, you have predicted strength on the vertical axis, you have experimental bond strength on the horizontal axis, you have the one-on-one line, and it's showing how with the different models that she's using, which ones are giving her a better behavior, and you can see how the GPR data points are getting closer to the one-on-one line. So this is something interesting, and I know some of my colleagues that have been looking into this K sub B factor really in depth. So she's indicating or she's highlighting what are some key variables. And again, I'll encourage you to reach out to her if you have some knowledge on this area and you would like to maybe provide her some follow-up questions with respect to the work that she did and I'm presenting today. The key variables in here that she indicates: the surface texture, anchorage length, and those four are found to be the most significant to impact the tau sub u value. The least impact, as she says, will be the FRP type, and then saying that maybe there are other values that are more critical to play a role into bond. So as you can see in here, she has a plot with those different variables that she worked in or she explored, and these are the values that she was able to get for the F values for each one of these variables. Like with anybody that does modeling, and we have seen some presentations today, you need to check how robust your model is. So this is how she was able to check on the robustness of her own model and do a sensitivity analysis to be able to see how sensitive her model is to these different things. And I see her that she's plotting bond strength versus different variables, F prime C, the depth, and the length of the of the bonded areas to see how sensitive it is when you change those variables. And it's showing that she had a very strong relationship related to tau sub u to k sub b, and especially when you have sand-coated and rebars, and the R-square value now is 0.8. And you can see in the plot in here, it has k sub b from previous studies. This would be an interesting information to be able to look a little bit more in depth. And then you have the bond strength on the horizontal axis and how she's plotting sand-coated FRP bar behavior, rib FRP bars behavior, and how she's linking that with the predictions that she has from her models. So in summary and concluding remarks from her work, she was able to develop the machine learning model that established a relationship between the bond-dependent coefficient K sub B, and this was taken from large-scale testing, and the bond strength tau sub U that came from a very simpler pool of tests of FRP reinforced concrete. She identified surface texture as the most significant variable that affects the bond strength, and that led to a very strong correlation between K sub U and tau sub U with an R-square value larger than 0.8 across various surface textures and fiber types. Also, she was able to emphasize the need for expanding the data set for future research to be able to explore beyond the current study limitations and enhance the model's applicability and accuracy. And I'm pretty sure she's probably exploring also how to use it in other situations where this technique can be used. And last but not least, this work highlights the importance of being able to conduct standardized testing protocols for FRP concrete bond strength in order to ensure consistency across the studies and be able to use that information to develop structural codes. And with this, that's the end of our presentation.